I'm going to talk a little bit about parallel circuit troubleshooting. I'm going to put a circuit up here for you. So get out your calculator. I don't need to do these. You need to know how to do these. Basic circuit here. Basic circuit here. We're going to look at our equivalent resistance first. So I'm going to have a little chart here. Just looking at our resistance for right now. I've got R1, it's 1.5 K ohms. R2, it's 5.1 K ohms. And R3 is 2 K ohms. Before we do any voltage or current measurements, we need to find the total equivalent resistance using our reverse. We need to find the total equivalent resistance using our inverse reciprocal formula. And what do I get for that? 733.8 ohms, total equivalent resistance. If I have an ohm meter, and I purposely did not draw a power supply here, if I put my ohm meter across my circuit, I will read 733, I'll round it up to 734 ohms of total resistance. So that's taking my ohm meter and placing it here. The problem with a parallel circuit is if I put an ohm meter over here, what will I read for total resistance? The same thing, 734 ohms. It doesn't matter where I put the ohm meter. I can put it here, or here, or here, or here. I'm going to read the same total resistance because they're in parallel. The meter doesn't care what's going on out in the real world. All the meter knows is, what is that total resistance? So, if we had an additional resistor in this circuit, however it became open, we will still read that same value of 734 ohms because it just doesn't matter. These resistors are in parallel. So that doesn't mean we can't troubleshoot it. It just means we have to troubleshoot it differently. So if I give my circuit a voltage, and let's say I give it 42 volts. Well, what do we know about voltage in a parallel circuit? I'm going to have 42 volts on each of these resistors. I need to find my current. If I have a total of 42 volts and a total equivalent resistance of 733.8 ohms, what is my total current? $57.2 milliamps. I trust you're doing these calculations because they need to become second nature to you when you get into the labs, quizzes, etc. You need to be able to solve these circuits. I have a total of 57.2 milliamps, so that's flowing through here. Well, we know that this current is going to get split up three ways. Small amount is going to go through R1, another amount is going to go through R2, and another amount is going to go through R3. If I take 42 volts and divide it by 1.5 kilo ohms, what do I get for current in R1? .28 milliamps. .42 volts, 5.1 k ohms for R2. What is my current? 8.2 milliamps. And if I have 42 volts and 2 k ohms, how much current do I have in R3? 21 milliamps. These three current values are going to add up to our total. 20, 40, 9, 57. Looks good. Our numbers seem to check. So now that I know the current flowing through each branch, if I get an open, what is going to happen to my total current or my branch currents? If I have an open, I will have no current flow. So now my new total with R2 open R1 is going to have 28 milliamps. And R3 has 21 milliamps. That is going to give me a new total current of 49 milliamps. So that is going to be my total over here. .49 milliamps. By measuring the total current, I can troubleshoot this circuit. The problem with looking at this circuit is this resistor is still going to be in here. So to look at it, you can't tell that it's open. When you measure the resistance, you're going to get the same resistance. When you measure the voltage, you're going to get the same voltage. If I put my voltmeter here, What am I going to get for voltage? 42 volts. The voltage across an open is the applied voltage. I have no current flow, but I still have potential voltage. I'm going to have 42 on these as well because my resistor is dropping that voltage. So my resistance and my voltage measurements aren't going to be as forthcoming as they were in a series circuit. However, by measuring this total current, and the easiest way to do that in our lab is to just put it right in between the power supply and the rest of the circuit. It's come straight out of the power supply through the meter into the rest of the circuit. Well, I now have 49 milliamps. And what did I have before I had an open? When all three resistors were working correctly, I had 57.2 milliamps. I'll just use 57 for a round number. Well, if I subtract my current that I have now from the current that I should have, I get a difference of 8 milliamps. Well, if we look at the current from our previous measurements, lo and behold, R2 is, the current through R2 is 8.2 milliamps. That's the difference I have. So now I can suspect that R2 is open, and I can calculate my new total resistance, equivalent resistance, with only two resistors, 1.5K and 2K ohms in parallel. When I punch those out in parallel, I get 857 ohms, which is less than my smallest one. So I should be able to measure that total resistance and verify that R2 is open. When we're measuring in a parallel circuit, which is what we're usually measuring, we do measure series circuits, we do troubleshoot series circuits, but if we have our supply and we have voltage going, let's say, to a light, and we have another voltage going to another light, and let's say we have three of them, but this one is open. It's an incandescent light and the filament broke. Well, this light here is glowing, and this light here is glowing. So if I have 120 volts AC, and I put my voltmeter here, what voltage am I going to read? My bulb is good. My load or my bulb is dropping full voltage. It's in parallel. I should read 120 volts. Same with this one. I should read 120. But now I have this open here. I have this bulb that's broken. What voltage will I read on that? Well, what voltage do I read across an open? I read 120 volts. So when you have something like a light bulb that is lit, you can tell if the load is working correctly or if it's open. But if you have a load like a heating element or a motor, and without some other test, if it's good, it's measuring 120 volts. And if it's bad or open, it's measuring 120 volts. So we have to be able to determine with other tests if our load is receiving voltage, working correctly. We may need to check current. One of the best tools is the clamp-on current meter, because regardless of what these current values are, if I clamp on here and check my current, I should read some current value. 2 amps, 1 amp, half of an amp, whatever. When I clamp onto here, I have no flow, so I have no current. And when I clamp my current meter here, I will read 0 amps of current. So, some different ways to test things. The labs that you will do for troubleshooting will be similar to the series circuit unit that we did last in DC1. We're going to build a couple of circuits. We're going to put some opens in it. We're going to put some shorts in it. We're going to make some measurements. And then we will do the lab with some troubleshooting boards. We will build a representative circuit, take some measurements on what our circuit should read, and then we'll test some troubleshooting boards to see what fault is in our circuit. So if you're suspecting an open, you might have to get out your calculator and do some figuring, but when we get to the lab, we will already have done that before we get the troubleshooting board. The problem with a short in a parallel circuit is they're usually going to be pretty easy to spot. If I have a true dead short across this voltage here, how much resistance will I have across my power supply? Remember, our total equivalent resistance is less than or equal to or approximately equal to the smallest resistance. Well, how much resistance is on a short? How many ohms? How many ohms of resistance is on a short? 0 ohms. If I have 0 ohms in parallel with anything, what is my total going to be? Going to be 0 ohms. I don't care if I have 500 million mega ohms. It's in parallel with 0. Anything in parallel with 0 is 0. My power supply is going to see that dead short. It's going to burst into flames. It's going to catch on fire. There's going to be smoke billowing out. We're going to know right away we've got a short. We have to look at them differently in our labs. The first lab that will be showing you the properties of a short in a parallel circuit, they're going to put a resistor in the main line And now we can put a short in our circuit, and we can take some measurements and we can see what happens. So without doing any numbers, if I short out this middle resistor here, well, this acts like a piece of wire. These two resistors in parallel with this will be 0 ohms, but I still have this mainline resistor, so my circuit will essentially consist of just this main resistor here. So I can put a short in and I can measure it and I can do some comparisons. Just a little bit more on the troubleshooting of parallel circuits. Remembering that those current values combine to the total current in our parallel circuit. Here we have 10 volts, 2 resistors in parallel. They're just drawn a little bit differently. Our 5 ohm resistor has 2 amps. Our 10 ohm resistor has 1 amp. These two are going to combine for a total of 3 amps total resistance. We're showing here just a little bit different way. We had you in the lab in the previous unit use different colors to show that we have 2 different paths of current, or as many resistors as are in the circuit, and these paths are going to combine for that total current that's going to help us when we're troubleshooting. Just another graphic showing that the current values add up. My total current value here is going to be the same as my total current value here, because here the currents come out and they split up. On this side they combine back together. So my total, this is also called the mainline current here as well. This is a question that shows up on tests and quizzes on parallel circuits on what happens when you add resistances in parallel. Well, what happens is the resistance goes down. It doesn't go up because we added a new path for current to flow. You have 60 volts in the first frame here, 130 ohm resistor. We have 2 amps of current. Here we add another resistor. We add another branch for current to flow. So now we have 2 amps in R1 and 2 amps in R2 for a total of 4 amps. Well, if my current went up, my resistance must have went down. That's our inverse relationship between current and resistance, because here our voltage stayed the same. Next one, we add a third resistor. It's also 30 ohms. We have 60 volts. So now we have 2 amps in R1, 2 amps in R2, and 2 amps in R3 for a total of 6 amps. Again, if our current went up, our resistance must have went down. And here we can see that when we have 3 30 ohm resistors in parallel, our total equivalent resistance is 10 ohms. So we started with 30, we added 2 more 30s, and our resistance went down. Adding another resistor in parallel causes the resistance to go down, not to increase. Hint, hint, you're going to see that on a quiz or a test in the future. Here we're just showing that our power adds up the same way for our parallel circuits. 30 watts generated. We're using 10 watts on the first resistor, 20 watts on the second resistor. Our power is the same formulas. Power adds up individually. Our total power is our total voltage times our total current. Both formulas should come up with the same answer so that we can check our answers. So troubleshooting, as we talked about a little bit already, if we have an open in the main line of our circuit here, we've got a 120 volt source. None of our bulbs will be lit. However, over here, if our open is in just one of our devices, the other devices will still receive voltage and current flow, but we just won't have any current flow in the one that's open. And if we have a short in our resistor, the text here reads, if you calculate the total resistance of this circuit, it will be 0 ohms. Anything in parallel with 0 is 0. This will cause the current to attempt to reach infinity. Whatever our voltage source is, it's going to try and reach infinite amps of current. The only thing limiting the current draw is any circuit protection, fuse, circuit breaker that you might have. Otherwise, this circuit will attempt to pull as much current from the source as possible, and you can see our guys having to put a fire out and the fire trucks come and all of that. So the first lab in this unit will discuss opens and shorts. The second lab will do some parallel circuit troubleshooting. Thank you.